Okay, assalamu alaikum. So what we are going to discuss today is heteroscedasticity. If you remember, we had talked about the assumptions that we've been using so far without much discussion. And we said we'll start talking about what happens if these assumptions don't hold. So we had in fact discussed the normality assumption and said that that was not really required if we had a large enough sample. Our OLS estimators were going to be approximately normal anyway, even if the error term was not normal. And that's because, does anyone remember why is that?
Sir,
Why?
beta becomes normal because of central limit theorem in large chapter.
Beta hat becomes normal.
Yeah,
Beta the constant.
hat OLS estimate.
G, and why does the central limit theorem apply to beta hat? Central limit theorem originally is a theorem about sample averages, sample means, right? So central limit theorem says that if you have X bar, you subtract the mean population mean that X bar is trying to estimate, and you divide by sigma, which is the population standard deviation of X. Then this whole thing, as n goes to infinity, is gonna converge to a standard normal. Okay. So X bar, if you remember, we derived the mean and variance of X bar. What was the mean of X bar and what was the variance of X bar? X bar is a random variable, right? It is a function of my sample X values. So what's the mean of X bar? And what's the variance of X bar? Who will tell me the mean and variance of X bar? And this is also a constant. G. Variance is 0 and mean is. G, speak up, please. Just unmute yourself and say.
So the expected value for X bar would be mu, and the variance would be 0 because it's rho square upon n. So as n approaches infinity, it becomes 0.
No, the variance of X bar is not equal to 0. We are talking about finite sample variance. We are not talking about the limit as n approaches infinity. Even you can see in that limit, the variance is 1. So actually, this side is slightly, I don't expect you to get it straight away. So ignore the right-hand side, the limiting distribution. Let's focus on the left-hand side first. So we have X bar, which is a random variable. We are subtracting its mean, which is mu, and dividing by sigma. So what was mu and sigma? So we had individual X variables, Xi, and these X variables followed a distribution with mean, mu, and variance sigma square, right? And this distribution could be any distribution. It could be a non-normal distribution. In fact, that's what this theorem is about. कि x की जो भी distribution हो, x bar की distribution normal हो in a large enough sample. So to understand this theorem, first we need to recognize that x bar is just the average of the n x values I have obtained in my sample, because x bar is simply summation xi over n, the sample mean, right? And because it's the sample mean, we should treat it like a random variable. It is a function of the sample x values that I have. So if it is a random variable, we can talk about calculating its mean, its variance, the distribution that this random variable takes. So distribution के बारे में तो ये theorem है, mean और variance we can simply calculate using this expression. So the expected value of x bar is going to be the same as the expected value of xi, which is mu. And the variance of x bar क्या होगी? If the variance of x is sigma square, we calculated this some sessions back. So variance of x bar is, you have variance of the right hand side. N is a constant. I can take it out of the variance, but I need to square it. So 1 over n square variance sigma x. And if if individual x observations in my sample are independent of each other, if I'm drawing these x variable values as a simple random sample from some population, so each x is independent and identically distributed, then I don't need to worry about the covariance terms. So the variance of sum of x is going to be the sum of the individual variances, which is sigma square. So the numerator is n times sigma square, the denominator is n squared, so you get sigma square over n as the variance of x bar. And so what is the standard deviation of x bar? You just take the square root. So sigma over square root n. ठीक है जी? Okay, now we need to understand what's happening here, and to understand that we need to first understand this whole thing, this ratio. Forget the square root n for a second, which is outside, and multiplying it. So this thing is a random variable minus a constant divided by another constant, right? So obviously the result is going to be a random variable, a normalized random variable, right? So there's another theorem जो I think implicitly आप जिसकी बात कर रहे थे. What's going to happen to this as n goes to infinity? There's a law of large numbers. What does that say? What's going to happen to x bar as n goes to infinity? What's going to happen to the term in this red box as sample size goes to infinity?
Sir, it converges to the expectation of x.
Sorry, it will converge to expected value of x, which is क्या symbol use कर रहे हैं हम उसके लिए?
Mu.
So आप कह रही हैं कि as n goes to infinity, my x bar, the random variable, is going to converge with probability 1 to this constant mu. Is that what you're saying? Well, that's what the law of large numbers says. ठीक है ना? कि x bar as n goes to infinity, the sample average converges to the population mean. So sample average is a random variable, population mean is a constant. So as n goes to infinity, the density function of the sample average is going to collapse at mu. It's going to take that value with probability 1, right? So effectively, this random variable becomes a constant mu as n goes to infinity. तो अगर ये mu के equal हो रहा है तो फिर इस पूरी expression को क्या होगा, ये जो red box में term है ratio. What's going to happen to this as n goes to infinity? बताएं भाई.
So it will become 0.
It should converge to 0, right? So as n goes to infinity in the limit, this whole thing is going to 0. Right? So by the law of large numbers. Now, so which makes the central limit theorem quite puzzling, क्योंकि वो कह रहा है कि वो 0 तो नहीं, as n goes to infinity, this whole thing when you multiply by square root of n, it is a non-degenerate. मतलब ये तो एक degenerate किस्म की आपका density function collapse कर रहा है to a single value. यहाँ पे हम कह रहे हैं कि अगर इस red box को आप square root n से multiply कर दें, so then you are not converging to some constant, you are converging to a stable distribution, which is the standard normal distribution, right? With the mean 0 and variance 1. So एक तो चीज ये, what is happening to this term as n goes to infinity? So n goes to infinity, this thing is going to infinity, right? So we have a term that is becoming really, really small. It is asymptoting towards 0, and a term that is going to infinity at a rate square root n, right? And so it so happens that when we multiply these two, so one term is exploding, becoming large and large, and the other term is becoming really, really, really tiny, going down to 0. And so when we multiply the two terms together, we get the result is that we get a standard norm. This thing, right? So why do we get a standard normal with mean 0 and variance 1? That is actually the easiest part. So because x bar had a mean mu and a standard deviation sigma over square root n, when I subtract mu and divide by, actually I can take the square root n to the denominator. So when I'm effectively multiplying by sigma over square root n, right? And so I had a random variable, I'm subtracting its mean and dividing by its standard deviation. The result is going to be, what's going to be the result of that? I'll get a new random variable with mean 0 and variance 1 when I do that, right? So mean 0 or variance 1 to is obvious whenever we do this to any random variable. When we take a random variable, subtract its mean, divide by its standard deviation, we get a new random variable with mean 0 and variance 1. The important thing here is the central limit theorem की real value है वो ये normality. So it is saying that if you have a sample average, that sample average, as your sample size keeps on increasing, वो original x की distribution कुछ भी हो, so this f could be anything in the entire statistical literature, as long as you know the x's. I mean, there are multiple versions of central limit theorem, but as long as the individual x's are independent, we are drawing independent random draws from the same distribution. The x bar is going to converge to normal, regardless of the starting distribution of x. So how does this apply? This is all a theorem about x bar. What happens to x bar as n goes to infinity? It's a limiting theorem. It's an asymptotic theorem. So the distribution of X bar approaches, and we call this convergence in distribution with a little d, as opposed to this convergence result, which was convergence in probability. So sometimes we put a little p to denote that under the arrow. So this was saying that the random variable is collapsing to a constant. It takes that constant value with probability 1. So uska jo density function hai wo collapse kar jayega as n goes to infinity. This thing, ye square root n agar andar na, right? You have constants here, so that thing is collapsing to 0. And this thing is saying that this thing is collapsing to जो भी distribution function x bar का originally है, it might be something very asymmetric, highly skewed, but as n goes to infinity, it will look more and more like that symmetric bell-shaped normal curve, right? X bar might, so the starting x side might even be a discrete random variable. It could be uniformly distributed, it could be an exponential, whatever. जो x bar है, that will look approximately normal in large samples, and that approximation will get better and better as n goes to infinity. As you keep on adding more sample, the density function of x bar, the sample mean, will look very close to the normal distribution. In fact, is theorem, if you take multiply both sides by sigma over square root n and add mu, you can also say कि हम ये कह रहे हैं कि आपका जो x bar है, that's going to converge to normal with mean mu and variance sigma square over n. Right? So sometimes लोग इस तरह भी state कर देते हैं इसको. The original statement is this of the theorem, but if you multiply both sides by sigma over under root n, यहाँ पे भी multiply कर दें तो आपकी variance sigma square over n होगी, and if you then add mu, the constant to both sides, you get a constant mu on that, and you get the additional terms here. So essentially this theorem is saying कि मेरा जो sample average है उसकी जो density function है, that's gonna be a normal density. Okay, so how does this apply to beta hat? So I'm start to either side. So does anyone have a response to that? So this is a theorem about the sample mean. How does it apply to beta hat? Anyone?
सर मुझे इस जो भी आपने एक्सप्लेन किया इसमें क्वेश्चन है.
Okay, go ahead.
इसमें जो मीन इक्वल 0, लाइक जो आपने नॉर्मल 0 1 शो किया उसमें 0 की सेंस मुझे समझ आ रही है. जो वेरिएंस 1 है उसको आप एक्सप्लेन कर सकते हैं वो किस तरह डिराइव किया, क्योंकि मुझे तो एग्जैक्ट समझ नहीं आ रही थी कि हम कैसे उस पर.
Variance 1 इसी तरह derive हुई है कि I have divided. So first I subtracted the mean from x bar, and then I divided by what? Divided by, अगर आप ये square root n इधर नीचे ले आए, sigma over square root n, that was the standard deviation. So of x bar. तो मैंने x bar का mean subtract करके उसी की standard deviation से divide कर दिया. So when I take a random variable, any random variable z, जिसकी वेरिएंस सिग्मा स्क्वायर है और उसकी स्टैंडर्ड डिविएशन सिग्मा है, तो इफ आई क्रिएट नाउ अनदर रैंडम वेरिएबल व्हिच इज दैट ओवर सिग्मा, तो इस न्यू रैंडम वेरिएबल की वेरिएंस 1 हो जाएगी, राइट? बिकॉज द वेरिएंस ऑफ w will be variance of z divided by sigma square. So sigma square और sigma square cancel. So that's the standard normalization thing कि आपने अगर एक random variable को normalize करना है, in fact आपने वो देखा होगा we talked about this chapter 6 के अंदर they talk about normalizing your y and x variables in a regression model. तो आप यही कर रहे होते हैं ना, you find the sample mean of each variable and their standard deviation. So you subtract the mean and divide by the standard deviation, and you get a normalized, a new variable which has a mean 0 and variance 1.
Okay.
So was there any other question? Okay, so then what's the answer to my question? How does central limit theorem apply to beta hat, the OLS slope estimator?
So we can use this for beta hat because the expected value of beta hat is beta, and the standard deviation is still sigma, and then we can normalize it.
Okay, but this theorem is essentially about sample averages, right? So beta hat is an OLS estimator. What relation does that have to sample averages? Matlab it's beta hat is a function of my sample y and x data, but is that a sample average? What is the sample average? How do you find sample average of something? बताएं भाई. Sample average calculate करने के लिए क्या करना होता है? What do you need to do? Anyone? Zona, just unmute yourself.
Yes, sir. Am I audible?
Ji.
Yes. Sir, the sum of all of the excess x present within the sample over the total population.
नहीं, वो तो x का sample average होगा ना, but sample average तो आप किसी भी चीज का ले सकते हैं. वो तो आप x बार का मुझे बता रही हैं कि x की sample mean value, you will add all the sample x values divide by n, you will get x bar. But अगर मैंने किसी और चीज का sample average देना, what does sample average basically involve? How do you find sample average of anything? What's the basic operation that you do? Because beta hat जो है आपका slope coefficient वो सिर्फ x पे तो नहीं depend कर रहा ना, वो x और y दोनों variables की values ही उसमें use होगी in calculating beta 1 hat. So it is you should think about the sample average as the operation. What does it involve?
Sir, do we take expected value?
No. Expected value और sample average में क्या फर्क है? यहाँ पे हमने लिखा हुआ था ना, we had said expected value of x bar, which is quite confusing because हम x बार को भी एवरेज कह रहे हैं, एक्सपेक्टेड वैल्यू को भी एवरेज कर रहे हैं, तो यहाँ पे दोनों काम ही हो रहे हैं. So how, what's the difference between the expected value and x bar? So ये x bar, so पहली चीज तो ये है कि this one is called the sample average or sample mean, ठीक है ना? So the word sample is important. This one you can call expected value, you can just call it mean, or you can call it population if you want to be very explicit that this is not the sample. You can add the word population. What's the difference between these two? Sample average तो अभी मैंने लिखा था, that's just gonna be summation xi divided by n. How do you find expected value? Expected value of any random variable, how do you find it? What's the formula for calculating the expected value? Is that also summation xi divided by n, or is that something else? बताएं भाई. This is a very basic question, so either some of you know the answer and you're not willing to share it with us, which is really bad, or you don't know the answer, which is worse. So, so which of these is true? So population mean या expected value का formula नहीं पता किसी को? That's like probability 101.
Sir, Fiza
Actually.
type something in the chat box.
नहीं, चैट बॉक्स में कितनी दफा, 1000 दफा मैंने आप लोगों को कहा है कि जब मैं बोर्ड पे हूँ तो चैट बॉक्स पे मत कुछ लिखा. Can you just tell us?
Yeah, so Fiza is saying that the expected value is the true population value and x bar is the sample mean.
नहीं, इसका फॉर्मूला बताएं ना, एक्सपेक्टेड वैल्यू मैं कैसे फाइंड करूंगा किसी
So
रैंडम
that's going to be x multiplied by probability of x.
x multiplied by probability of x. What x? The random variable x या?
Yeah, so xi हो जाएगा.
हाँ, so मतलब है कि आप ये random, अगर if there's a random variable x, the fact that it is a random variable means it takes more than one value, right? So वो जितनी भी values लेता है उसको अगर आप small x से denote करें तो all possible values that it takes multiplied by their probabilities and then added together. So there is a summation involved here also, but you are summing over all possible values that my random variable x takes. For each value you multiply it with its associated probability, the probability that x equals little x, right? Now you can see the who will tell me. So this is the population mean, this is the expected value, this is the sample mean or the sample average. What's the similarity or difference here between the two formulas? So similarity की अगर पहले बात कर लें, do you see any similarities? You find no similarity? So this is on the left hand side, you have got the expected value of x, the population mean of x. On the right hand side, you've got the sample mean of x. Is there any similarity in how you calculate the two means?
So
someone
both
was
of them
going
are
to-
summing up xi's, but the expected value is also multiplying another with it. So that's the probability.
Okay, so you are saying that both of those formulas involve a summation. So I am summing something up. Okay. And I am in calculating the population mean, I am doing a weighted sum where the weights are probabilities. So I'm taking each possible value that X can take and multiplying that value with its probability. So I'm taking a weighted sum. But the important thing is that I cannot calculate the sum until and unless I know the probability value. ठीक है ना? अगर मुझे इस रैंडम वेरिएबल की प्रोबेबिलिटी डिस्ट्रीब्यूशन पता है, जो कि स्टैटिस्टिक्स में तो कभी नहीं होता. I mean, you only have the data sitting in front of you. You don't have the probability distribution. But अगर आपको probability distribution पता हो, जैसे X is a coin toss random variable, or it's some random variable with known probability distribution, then you can use those probabilities to calculate the expected value. ठीक है ना? Yeah, if X is a random variable which is defined in terms of another random variable जिसका mean हमें पता है, so we can use properties of expectation to calculate the expected value of this. But you need to know either the probabilities to calculate the expected value by definition from first principles, or you need your random variable to be a function of some other random variable with known expected value. ये वाला सो सिमिलैरिटी क्या हुई? सिमिलैरिटी ये है कि दोनों में हम सम कर रहे हैं x की वैल्यूज. यहाँ पे x की वैल्यूज को प्रोबेबिलिटी से मल्टीप्लाई कर रहे हैं. यहाँ पे क्या कर रहे हैं हम? यहाँ पे भी you can say कि we are doing a weighted sum, right? But यहाँ पे probabilities नहीं यूज कर रहे हैं. यहाँ पे हम हर वैल्यू को 1/n से essentially हम इक्वल probability हर वैल्यू को असाइन कर. So we are doing a sum of xi times 1/n, right? So that's what the sample average is doing. So they're both taking a sum. The difference, I've already said the difference. एक में probabilities use हो रही हैं, दूसरे में probability हमारे पास नहीं है, तो हम simple उसकी empirical probability sometimes लोग कह देते हैं 1/n empirical distribution. Basically हम हर वैल्यू को उसकी फ्रीक्वेंसी, relative frequency से मल्टीप्लाई करते हैं. So the difference is कि we are summing the values and dividing by n. यहाँ पे कोई n नहीं, यहाँ पे probabilities. और यहाँ पे n की sense इसलिए भी बनती है because we have a fixed sample of size n. So यहाँ पे कोई सैम्पलिंग नहीं हो रही, यहाँ पे तो प्रोबेबिलिटी डिस्ट्रीब्यूशन है और उसको यूज करके हम एक एक्सपेक्टेड वैल्यू निकाल. ठीक है जी? Is that clear? Now tell me how would you apply central limit theorem, which is a theorem about sample averages? How would you apply it to beta hat? So sample averages में क्या involved है? We are so if we want to find the sample average of something, we need to add the different values of it in my sample and then divide by n. That's how you find the sample average. So beta 1 hat जो है, is that a sample average? What's the formula for beta 1 hat? Anyone? Simple regression में जो आपका beta 1 hat होता है, उसका क्या formula होता है? बताओ भाई. Afreen, Salman,
Sorry, I can't seem to remember.
Zona. Does anyone remember beta 1 hat का formula?
Sir, is it that formula x1 minus x वो जो bar into y1 plus y bar divided by x1 minus x bar whole square?
So tell me again. There's a ratio in the numerator. You've got what x1 xi है xi minus x
G sir,
bar
xi.
times
y
ठीक है और नीचे क्या है डिनोमिनेटर में
summation xi minus x bar whole square.
G sir.
xi minus x bar ठीक है ओके सो नाउ ये फॉर्मूला है जी बेटा 1 हैट का सो ये अब आपको सैंपल एवरेज लग रहा है कहीं से इस पे सेंट्रल लिमिट थ्योरम अप्लाई कर दें या ना करें दैट्स द क्वेश्चन So beta 1 hat doesn't look like कि मतलब इसके अंदर सैंपल एवरेज यूज तो हो रहा है इसके फॉर्मूला में बट वो फॉर्मूला के अंदर एम्बेडेड है सो can we say beta 1 hat itself is a sample average of something? बोले भाई
So I don't
अच्छा
think
so
we can.
you don't think so summation किस चीज की हो रही है summation इस पूरी चीज की हो रही है ना so अगर हम इस पूरी चीज को w कहते हैं wi so you take the value of x subtract its sample mean multiply by the value of y and you call that thing in the curly brackets you call it wi so beta 1 hat जो है वो w को सम तो कर रहा है तो सैंपल एवरेज करने के लिए और क्या करना चाहिए उसको अब क्या रह गया पीछे
So I think 1 by n से multiply करना होगा.
you need to divide by n right so divide by n नहीं कर रहा so उसके लिए हम क्या कर सकते हैं वो भी इतना कोई मसला नहीं है because we have a ratio तो हम न्यूमरेटर और डिनोमिनेटर दोनों में divide by n कर सकते हैं right we can multiply by the same number 1 over n ठीक है so now you can think of beta 1 hat I mean think क्या करना अब तो obvious ही हो गया मतलब beta 1 hat is a sample average in the numerator and in fact there's another sample average in the denominator as well right so denominator में भी आप एक चीज को sum कर रहे हैं और फिर divide by n कर रहे हैं so अगर इस चीज को हम let's say z कह दें तो denominator में भी एक sample average so my beta 1 hat is not a single sample average it's a ratio of two sample averages so the question is we know that one sample average follows approximately normal distribution as sample size increases a sample average behaves like a normal random variable would a ratio of two sample averages also behave like a normal random variable so the answer is that yes because नीचे जो है this thing is going to converge as n goes to infinity this thing by the law of large numbers is just going to converge ये क्या चीज है ये sample variance है of x so ये जो sample mean वाला part है उसको अगर आप expected value से replace कर दें यहाँ पे भी एक सैंपल मीन आ रहा था, वो भी एक्सपेक्टेड वैल्यू से रिप्लेस हो जाए. So it's going to converge to this thing, which is the population variance of x, which is sigma square, some positive number, right? So the denominator is converging to a constant. अगर मैं न्यूमरेटर को क्योंकि इसकी जो वेरिएंस है उसमें डिवाइड बाय स्क्वायर रूट n आ गया, तो न्यूमरेटर को अगर हम appropriately scale कर लें तो that is going to converge to standard normal. So yes, beta 1 hat is a ratio of two sample averages, and the central limit theorem, which applies to any sample average, will also apply to the sample average, the numerator wali W bar. And so W bar को आपको बस appropriately scale करने की जरूरत है. So if you multiply it by square root n, you will get, so central limit theorem will give you the result के this is normal. This is converging to a normal. ठीक है जी. Any questions? So central limit theorem implies not just beta 1 hat, any beta in fact is converging to a normal distribution, being a function of sample averages, and therefore it is approximately normal in any finite sample, a large finite sample. ठीक है जी. So ये तो हमारी normality assumption होगी. So we don't need to assume that the error term is normal to get the result that beta hat is normal. Why is the normality of beta hat important to us? How did we use the fact that beta hat was normal? Or where did we use the fact that beta hat was normal?
So in hypothesis testing.
जी, hypothesis testing में किस तरह use हुई normality beta hat की? How exactly did we use it?
With the t-stat.
T-stat was just using beta hat minus C divided by standard error. So it was a ratio involving beta hat. तो T-stat की लेकिन जब हमने critical value find करनी थी, जब हमने ये decide करना था कि ये T-stat जो है इसकी p value बहुत कम है या ज़्यादा है, can I reject the null hypothesis at 5% significance level? तो वो जो 5% significance level का associated rejection region जो हम बना रहे थे, that was under a probability distribution, right? It was under a t distribution. तो वो t distribution normality, अगर beta hat normal नहीं होगा तो आपका t stat will not follow the t distribution. So आपका rejection region, अगर आप t distribution को use करके अपने critical values और rejection region निकाल रहे हैं, तो you will get incorrect answers. So the T-stat follows the T distribution only if beta hat follows a normal distribution. Similarly, your F-stat follows an F distribution only if beta hat follows a normal distribution. So normality of beta hat is important for doing any kind of hypothesis tests. जो hypothesis tests हमने learn किए हैं इस course में, they depend on beta hat being normally distributed. So अगर error term normal ना भी हो, in beta hat will still be normal due to central limit theorem and due to the fact that it is a function of sample averages. It will be normal in large samples. So as long as we are working with large samples, we don't need to assume the normality of the error term to be able to do hypothesis tests. Okay, is that clear? Any questions before I move on to the next point? Okay, so what is the next point? The next point that we want to discuss is this homoscedasticity assumption, which was variance of U given the X variables equals sigma squared. So the error term U takes the variance of the conditional variance of the error term is the same constant sigma square, meaning के आपके पास n different observations हैं. Each observation has its own error term value. So there are n error term random variables u1, u2 all the way up to un. हर error term की variance है conditional on the x value. All of those variances are the same positive value sigma square. Right? That's the constant variance or homoscedasticity. So what happens when this assumption is violated? Well, we get heteroscedasticity. So we get heteroscedasticity when this does not hold, and the variance of u given x is a function of the x variables. So the variance of u actually is not independent of the x variables as assumed by the assumption, a homoscedasticity assumption. Instead, the variance of u is a function of the x variables in my regression, at least one of them, right? So I can write heteroscedasticity either as this, or I can simply say that my sigma square for different error terms, I will get different variance values. So the sigma square is not constant for each error value, for each error term. Okay, how do you assess whether or not the homoscedasticity assumption is justified for your regression model? So I've got a regression y equals beta 0 plus beta 1 x 1 plus u. How do I tell whether the error term in my regression is homoscedastic or heteroscedastic, whether its variance is related to x variable or it's independent of x? So you can do you can either eyeball the scatter plot. So आप अपने scatter plot में assess करने की कोशिश कर सकते हैं. That's a loose kind of visual test, quote unquote test. मतलब you can just inspect the scatter plot and see whether the variance looks the same or different as the x variable value changes from left to right. दूसरा तरीका ये है कि there are formal statistical tests as well. So error term पे directly तो आपके पास data नहीं है, but you can use your OLS residuals to try and test whether the variance of u seems like a function of x variables or not. In fact, to see that test more clearly, so this is the variance of u. We need a variance of random variable u conditional on some variables. इसको अगर मैंने expected value terms में लिखना हो तो what is this variance going to be equal to? Variance of a random variable equals what? Is there a relation between variance of u and expected value of u? Is the question, I guess, that I'm trying to ask. वेरिएंस और एक्सपेक्टेड वैल्यू में क्या रिलेशन?
Sir, variance is like the deviation from the expected value in a way.
It's the expected value of that deviation squared, right? So variance of x is simply expected value of x minus mean of x squared, right? So actually दो expected values are in this. ये एक अंदर आ रही है to calculate the deviation, then you square the deviation, then take the expectation again. In fact, if you simplify this, if you open out, square the things inside and then apply the expectation, you also can write this as expected value of x squared minus e of x squared. आप लोगों ने ये expression भी देखा होगा. So variance of x can be written as expected value of the variable squared minus the square of the expected value. So यहाँ पे similarly we can write this as expected value of ui squared given the x variables minus the conditional expectation of u given x squared. ठीक है ना? So एक x variable नहीं है, x से ज़्यादा है. So let's just write it as a horizontal dash. Okay, now this thing, if the zero conditional mean assumption holds, this is equal to 0, right? So the error term, if the error term is mean independent of the x variables, and this conditional expectation function is always 0, that I can drop. And so the variance of u is simply a question. So whether or not the error term variance is or is not a function of the x variables is simply a question of whether the error squared, ui squared, whether it is on average related with those x variables. So इस regression model में whether the error is homoscedastic or heteroscedastic is simply a question of I obtain the OLS residual u hat and then I run a regression of u hat squared on my x variable. And then और अगर एक से ज़्यादा x variables थे original model में तो वो सारे मैं इधर डाल दूँ and then test for their joint significance. Right. So if you had plus beta k x k, it was a multiple regression. So you would have alpha 2x2 plus alpha k x k. Now जो joint significance का test है, the null hypothesis there is that alpha coefficients are all equal to 0, the slope coefficient, right? And so if all of these coefficients are equal to 0, then what can we conclude about the homoscedasticity of this error? So I estimate this regression using OLS, obtain the OLS residual u hat, square, obtain the squared residual, and then regress the squared residual on the original set of x variables. Okay? So this is the two-step regression, the second step regression that we are running. And then I'm saying कि अगर मैं joint significance test करूँ अपने x variables की in the second regression, what would that tell me about the homoscedasticity of this error u? Null hypothesis क्या बताएगा? If the null hypothesis is true, what does it imply about homoscedasticity?
So does that mean that X variables are uncorrelated with the U hat?
Not with U hat, with U hat squared. Dependent variable आपका U hat squared है ना?
Yes, I got it.
Okay, so is that good or bad for homoscedasticity? Does it go in favor of homoscedastic error or not?
So why would there be a link between that? वो अलग चीज है, ये अलग चीज है.
ये आपके सामने लिंक लिखा हुआ है बोर्ड के ऊपर. ये जो कंडीशनल एक्सपेक्टेशन रिग्रेशन जो है, isn't our regression model a specification of the conditional expectation? We've seen that before, right? When we write a regression model, उसका जो x variable वाला part होता है, that is simply expected value of y given these x variables, right? ये तो हमने पहले शो किया हुआ. So conditional on the error term, uska conditional expectation being 0, I can write the conditional expectation of y is simply beta 0 plus beta 1x all the way up. So यहाँ पे हमारे पास एक conditional expectation function आ रहा है of u squared, और हमें ये नहीं पता कि वो conditional expectation function जो है वो किसी constant के equal है या is it a function of one of the x variables. But we can actually test that. So we can run a regression. So this conditional expectation function is equivalent to running this regression, right? Where this is your dependent variable, like here, this is your dependent variable y. U की हमारे पास data नहीं है, so we instead of u we use a proxy u hat. So u hat squared को मैंने regress कर दिया है सारे x variables में, right? So I am effectively trying to estimate this function in my sample. So I get a set, I can run this regression after I have obtained u hat squared, the residual from the first regression, or the squared residual from the first regression. I can run equation 2. I can estimate the alpha coefficients, and then I can test the joint significance of the slope coefficients in this model. What will that test tell me? That was the question I was asking. तो ये null hypothesis आपको क्या बताएगा? अगर सारे slope coefficient 0 हैं, तो इसका मतलब है कि ये x variables are not correlated with u hat squared, ठीक है? And what does that mean for my original regression? Equation 1. बताएं भाई. So if h naught is true, what can we say about this variance function?
So if H naught is true, then
Yeah,
should
for the 1 millionth time, I am saying, please don't write in the comments box. Afaq, why don't you unmute yourself and just say what you have to say?
So if the hypothesis is true, it means that the correlation between the u and the x variables is 0. So they are not correlated. So the variance would be sigma squared and it will be homoscedastic.
So basically, you only have this constant left in this regression. All of this is 0. So x variables together don't explain any variation in u hat squared, in u squared. So I can say that this thing is just a constant, right? That's what this regression is telling me. Okay, u hat squared has no relation with the x variables, which means that I can say that the conditional expectation of u squared has no relation with the x variable, which was this conditioning set over here. So this thing is just a constant. If I were to regress u squared on the x variables and the slope coefficients were all 0, that means that this function is just a constant value, right? And if it is just a constant, that means the variance, the variance function, the conditional variance of u given the x variables is a constant. It's not a function of the x variables. And so we are the error term in model 1 is homoscedastic. So if the null hypothesis is true, the null hypothesis we are testing is actually the homoscedasticity hypothesis. So if the null hypothesis is true, we conclude that the error term in model 1 is homoscedastic. If the null hypothesis is rejected, meaning that at least one of these slope coefficients is non-zero, then we have to conclude heteroscedasticity. Then the homoscedasticity is rejected by the data. Okay, so that's a simple way of testing whether or not the homoscedasticity assumption makes sense, whether it holds for the regression model that you want to estimate. So you just need to run the second regression, run these two regressions, and in the second regression, obtain the F test of joint significance. Okay, there's also there's also a visual, as I said, a visual way of inspecting whether homoscedasticity assumption makes sense or not. So to think about that, let's think about a regression of savings, how much you save as a function of your income. And so income is the X variable, savings, which is the income left over after subtracting all your expenses, is the Y variable. And so if you think about the scatter plot, and if you think about the fact that this variance of u is the conditional variance of u is actually equal to the conditional variance of y, which is something that we saw in the previous lecture. So the constant variance assumption, even though the homoscedasticity assumption as stated is making that assumption about the error term u, it is also making that assumption about the dependent variable y. So if u has constant variance, constant conditional variance, so does the dependent variable y. So error term पे तो हमारे पास data नहीं है, but y variable पे तो है ना, तो हम y variable को plot करके देख सकते हैं against the x variable कि उसकी conditional variance को क्या होगा. So you have income on the x-axis, savings on the y-axis, and then the question is कि what happens to savings as income increases. What do you expect will happen? So as people's incomes increase, would you expect them to save more or less?
Save more.
Okay, so you are saying that this beta 1 should be positive. As income increases, you should be saving more. And let's say beta 0 is also positive. Let's say beta 0 तो income अगर आपकी 0 है तो फिर आप save तो नहीं कर सकते. चलो इसको negative. Negative savings just means that you borrow, right? You are borrowing against future income. ठीक है जी. So in any case, we are not likely to observe people with zero incomes. So typically, if somebody says, if a working age adult says that they don't earn anything, especially given के income, we are not by income, you can include not just the income that you earn from your labor, but also any transfer income, income that you get from others, from household members, from government, welfare payments, etc. So income की observed range of values जो है वो positive spectrum पे lie करेगी in most cases. So anyway, we've got a positive relation between income and savings. ठीक है जी, that positive relation is simply this beta 1 coefficient here. But वो तो what is this line telling you? ये आपको क्या बता रही है? ये variance तो नहीं बता रही भाई. What is this line telling you? This is telling you the conditional expectation of the Y rate given income, right? This is not telling you about the variance. Variance का कैसे पता लगेगा? So if you want to know what is happening to the conditional variance, you need to think about what happens when you fix X at some value. Let's say you fix income variable at some level, income 0, and then you look at the savings corresponding to income 0. Now this regression line tells me that the mean saving corresponding to income 0 is this level, right? So that is simply the expected savings when income equals income 0. But there are people with this level of income who save more above average savings than jinki or jinki below average saving, right? So you will get in your sample and in your population, you will have individuals with values of savings above and below this mean level. And in fact, we can draw a distribution. Right. So agar, well, this is all. Right. So this is a skewed distribution. And at inc 0, this is how it looks. Now the question about heteroscedasticity is conditional distribution. So this is the set of values. This distribution tells us the saving values corresponding to inc 0. There's a whole range of saving values corresponding to different individuals. Is distribution function की एक variance है. Let's call it sigma square 0. Right. So the homoscedasticity assumption is asking, is really assuming कि ये वाली जो variance है, जितनी वेरिएंस आपको सेविंग्स में लो इनकम लेवल पे नजर आ रही है, उतनी ही आपको वेरिएंस नजर आएगी एट हाई इनकम लेवल, एट इनकम 1. So the question really is that the case or not? Right? What's your expectation? High income levels पे क्या होगा? So on average, people would save more. So that average relation between y and x is shown by this regression line. So you will have the average savings at inc 1 equals saving 1, this point, which is greater than saving 0. But homoscedasticity assumption is not about the average, it's about the variance. So what's going to happen to the variance of savings at higher income level? How do we think about that? Yeah, what do you think about that? मतलब again you will get a range of savings values. अब आपका income level बढ़ गया है इसके मुकाबले में. So think of these as super rich people, Mia Manshahs and Jahangir Tareens and whatnot. What would you expect to see? What kind of savings behavior would you expect to see at high income levels?
High savings, but they are not.
Yes, sir.
High
Extra high
savings.
savings.
नहीं, high savings तो हो गया ना. On average, these people save more. So people with higher net worth, higher incomes save more on average. ये तो इस point और इस point की कहानी होगी. So when we move from low income to high income, we move from low savings to high savings. That's this positive relation. हम ये पूछ रहे हैं कि जो हाई इनकम लेवल के लोग हैं, let's say there's a subpopulation of 20,000 people who are high income in the economy. उन 20,000 लोगों में जो सेविंग्स हैं, एवरेज सेविंग लेवल तो ये है, लेकिन कुछ लोग बहुत ज्यादा भी सेव कर रहे हो सकता है इस एवरेज लेवल से, कुछ लोग हो सकता है कम सेव कर रहे हो. तो वो जो वेरिएशन हमें नजर आएगी between the minimum saving at this income level and the max saving, वो वही होगी जो यहाँ पे नजर आ रही थी, उससे ज्यादा होगी या कम होगी. That range of savings levels.
Sir, it may be more because with lower income level, there is a lower percentage level of saving too. Like in middle class, we can save a limited amount, but with the higher income, with the higher richer group, the bell curve may be having a broader bell या फिर वो जो आपने curve सा बनाया है, because they can afford to save the highest amount in percentages even, in thousand or billions instead of thousands only that middle class can save.
Right. So exactly जो आपने ये बात की ना कि so ये जो बेल शेप कर्व, इसी तरह का एक कर्व बनेगा यहाँ पे भी, लेकिन उसकी बेस जो है वो ब्रॉड हो जाएगी. We will need to stretch it out. Why? Because these richer guys can either spend all of their income and save very little, so they could be saving zero out of this income, so they could be buying luxury houses, yachts, I don't know, whatever rich guys spend their incomes on. And then you could have some rich folk who don't spend anything, who are just so you have people who are lavish in the lifestyle, and people who are frugal despite being very rich, and they might be saving all of their income, right? So unka saving level yahan pe, right? So you have, just because you have a lot more space over which to save, इन लोगों के पास इतनी space नहीं, right? So अगर maximum भी save कर लेंगे, सारी income तो नहीं save करेंगे. They will still need to spend on housing, shelter, clothing, food, basic necessities के लिए तो spend करना है. तो वो basic necessities के लिए जो आपने spend करना है just to survive, वो अगर आप निकाल दें और income में पीछे margin ही थोड़ा सा बच जाए, जिसमें ठीक है अगर कोई lavish है तो वो शायद सारा उसमें से spend कर दे, अगर किसी कोई frugal है तो वो कम. So basically that range is smaller than what's available here, just because the income level, that space over which you can save minus the basic necessities is much larger. right? So we would expect that there will be a similar, there will be a range of behaviors that we will see with respect to savings. But that range that we will observe, the variance, the spread of savings is definitely going to be bigger. So sigma square 1 will not be the same as sigma square 0. We would expect it to be bigger. Right? So इसको आप scatter plot में फिर किस तरह देख सकते हैं कि आपकी से variance, conditional variance same है या नहीं है? If you remember, we had said that so there's a positively sloped line. Typically, आपका जो scatter plot है, your data points lie in a cloud around the regression line, right? So this kind of cloud indicates constant variance, right? मतलब यहाँ पे कुछ थोड़ी सी observations हैं extreme ends पे, यहाँ पे ज़्यादा observations है, but थोड़ी observations होने का मतलब ये नहीं है कि उनकी variance कम है. We just had fewer of them in our sample. So this corresponds, if you have like an American football, like a symmetric oval shaped, if you can, आपके पास वैसे तो data points हैं, but अगर आप उनके एक outline बनाना चाहें, which contains all those points, if that looks like this, that suggests more or less homoscedastic behavior. मतलब the variance of the y variable is likely to be the same at different values of x. But if you have like that savings versus income जो अभी हम बात कर रहे थे, उस केस में आपका scatter plot कैसा लगेगा? In that case, one side will have more variation in it compared to the other side. So then it won't look like a symmetric cloud of points. You will have larger variation on one end as opposed to the other. So उस वक्त आप अगर outline draw करेंगे तो it will look some non-symmetric thing like this. So that suggests heteroscedasticity or y variable variance that is changing with the values of the x variable.
Sir?
Hey.
So you just shared that for richer people, the variation might be more. So this will defy that that instance, right? It's oval shaped.
Sorry.
And for richer people, the variation in savings.
So वो oval, sorry, एक second. Oval shape जो है वो इस example के लिए नहीं है. इस example के लिए ये red shape.
Okay.
जी. So I am saying कि अभी जो हमने example discuss किया है ना, वो तो हम कहते थे कि heteroscedasticity होगी उसमें. You will see more variation at high income levels compared to low income levels. So that corresponds to this red. That's a heteroscedasticity. Your variance is increasing as x increases. Oval shape was when you don't have heteroscedasticity, when the variance is the same at different values of x.
Yes.
And maybe so basically the vertical space you have here is the same on both extremes. And middle में थोड़ी सी ज़्यादा हो जाती है, but you know that's just because we observe more data points. N is higher in the middle as opposed to the extremes. Okay. Now, why do we care about homoscedasticity, whether or not this assumption holds? What does that buy us? So that's an important thing. Let's discuss that before we end today's lecture. So what if this assumption holds? What do we get? If you remember, we said if homoscedasticity holds, so one thing that we in which we used this assumption was in deriving the formula for variance of beta. That was also conditional variance. So beta hat j की variance is equal to sigma square over SSTJ times 1 minus R square j. ठीक है जी. So ये वाला जो फॉर्मूला है, this was derived under the homoscedasticity assumption. अगर ये assumption नहीं hold करती तो then if this assumption is not true, then this formula is also not true. And you need to use a much more complicated formula, which we can't write as a simple expression. We need to use matrix notation for that. So this is your conventional standard error formula derived assuming homoscedasticity, right? So under heteroscedasticity, this formula is incorrect. Invalid, it gives inconsistent estimates, whatever. So उसकी implication क्या है? The implication is कि variance of beta hat use होती है in hypothesis testing. So वो जो आपका t stat है, उसके denominator में standard error आ रहा होता है, statistical significance का जो t stat, and that standard error is simply square root of this. So so if this formula gives you incorrect standard errors, the t stats are also going to be incorrect, and you will derive incorrect conclusions. Again, you will not be able to do hypothesis testing if you don't have the correct standard error of beta. Can't do T and F tests. So basically the same kind of implication जो normality assumption की थी. In the case of normality, we said don't worry about it. Just get large enough sample. Beta hat automatically normal हो जाएगी. इस case में large sample doesn't help. You need a correct formula, a formula that does not rely on this assumption. So there are such formulas. We will use robust standard error. Calculate robust standard error. In Stata, you can simply say comma robust. So regress y x1 x2. If you want robust standard errors, you say comma robust. Right? So Stata will know, okay, I don't, in order to report standard errors, I don't use this formula, which is assuming homoscedasticity. So I should use a formula which is robust to heteroscedastic errors. So that's one implication of this assumption. The other implication was, and this is the more serious problem, if our variances are not correct, variance of beta hats, we have a real problem. We can't do any hypothesis testing, right? We need to get correct standard errors. So uska solution is available. You don't need to, so you can continue to use OLS for obtaining point estimates. उन point estimates की सिर्फ standard error calculate करने के लिए आपको एक different formula use करना पड़ेगा, जो कि literature में available है, Stata के अंदर coded है, it's easily available, right? What is the other implication of a violation of this assumption? So if you remember, this assumption was also used in deriving the, it was one of the required assumptions for the Gauss-Markov theorem. The result that OLS is the best minimum variance linear unbiased estimate. So दूसरी implication heteroscedasticity की, homoscedasticity की implication ये थी कि OLS is blue. Heteroscedasticity से क्या होगा OLS is not the best linear unbiased estimate. In fact, there is another estimator out there which we call generalized least square, weighted least square. Weighted least square is a special case of generalized least square. So GLS has a smaller variance. So if you have got both of these estimates, the GLS estimate will have a smaller variance than the OLS estimate. And they're both linear and unbiased. So there's a theoretical reason for preferring GLS over OLS. Well, in practice, people don't abandon OLS because there's another linear estimator available with theoretically smaller variance. So even though there is a theorem, there's a result which says कि अगर आपकी error heteroscedastic है तो आपको OLS की बजाय GLS estimates GLS use करना चाहिए to obtain your estimates, beta hat estimates. But this is not used in practice. So in practice, अगर आपके model में heteroscedasticity है, so people will test for heteroscedasticity, and then they will just use OLS with robust standard error rather than use the generalized least squares. ठीक है जी.
Sir, what does blue mean?
Sorry. That's a good question. So we talked about that in the last lecture. Blue means best linear unbiased estimate. Any other questions? Okay, so this is all from chapter 8 in your textbook. So do read chapter 8. And if you have any questions, I'm around.
Thank you, sir.